I'm John Dale. The topic is Design Considerations for Grid-Neutral Schools. This is what you need to know. This brief talk is intended to be an introduction to the process of designing sustainable school facilities and investigates the potential of achieving grid neutrality. Several years ago, the state architect of California, David Thorman, began advocating the concept of grid-neutral schools as an achievable objective for reducing energy consumption in public school buildings. The concept is simple. Design buildings and campuses that offset the consumption of electricity from the grid through on-site independent energy creation and energy savings. While this concept does not take into consideration the full range of strategies required to achieve zero net energy, it similarly requires a balanced, holistic design approach to be successful. The State Architect's Grid-Neutral Schools program is one of a number of expanding zero-net initiatives that are increasingly influencing the design and construction industry in California. The underlying impetus behind the push for grid-neutral schools is the increasing stress on energy resources due to increasing consumption and the environmental effects of global warming, which is predicted to impact the global environment over the next 50 years. The Intergovernmental Panel on Climate Change predicts significant increase in average temperatures, 3.5 to 5 degrees Fahrenheit, over the next 50 years. Based on this trend, a typical school might experience a 50% reduction in heating load, but a 45% increase in cooling loads, resulting in significant increases in energy costs. How could a typical urban school be designed, built, occupied, and maintained as grid neutral? In response to this changing context, Harley Ellis Devereaux's education studio, in conjunction with its partner company Greenworks Studio, decided to revisit one of its recently designed school buildings, a typical urban elementary school in Los Angeles, to see how the impetus of grid neutrality would change the design approach. Some of the key characteristics of these schools create challenges for conventional, sustainable strategies. For example, these buildings tend to be 2 stories. They have double-loaded corridors, single-aspect classrooms, rooftop package units for each classroom, very limited acreage for landscape and playgrounds, tight space allowances, and low grossing factors, tight construction and operating budgets, and a typical inland California climate, very hot, dry daytime temperatures, cooler nighttime temperatures. We used one of our recently completed projects, the Los Angeles Unified School District's new Valley Region Elementary School number 12, as a case study to understand what measures would be required to achieve grid neutrality. This school was designed under the Coalition for High Performance Schools, that is CHIPS program, and already meets recognized criteria for energy conservation and sustainability. With a capacity of 650 students and a 3.5-acre site, the facility incorporates the following features: all north and south-facing classrooms, exterior shading on south-facing windows, light shelves at classroom windows, low LPD lighting systems, high-performance rooftop package units, high-performance glazing, operable windows for limited natural ventilation. Using software simulation, we analyzed a number of factors to assess the school's predicted performance based on the CHIPS performance goals it had been designed to achieve. This was then measured against a higher performance grid-neutral model to define the delta to be bridged through enhanced design measures. The investigation included a number of different models: climate analysis, thermal modeling, human comfort models, shading and daylighting studies. A customized energy model was developed to measure occupancy, lighting, and plug load consumption profiles, outside lighting, natural ventilation strategies. This modeling provided a way of measuring total energy consumption and energy use intensity, kPTU per square foot per year, the standard benchmark for energy performance. This axonometric view of the school indicates a total roof area of 30,000 square feet. Typically, a maximum of only half of the roof area is available for photovoltaics, and often considerably less, especially where the use of individual rooftop package units, one per classroom, is employed. The minimum area of photovoltaics required to reach grid neutral on a traditional calendar year is 14,000 square feet. The minimum area of photovoltaics required to reach grid neutral on a multi-track or year-round calendar moves up to 18,000 square feet. Based on the typical performance of commercially available photovoltaic panels, we need a lot of real estate if we are depending solely on photovoltaic arrays to balance energy use on a tight urban school site. A balanced approach suggests the need for additional, significant measures. There are a variety of ways to enhance energy performance offered by this building type in a hot, urban Southern California valley. Evaluating these options and assessing energy needs, it was determined to focus on some features that would most effectively enhance the performance of the building: skylights, thermal chimneys, and night flushing. Other potential options were set aside due to their limited viability or unknown conditions requiring further research. For example, wind turbines were set aside as an option because the combination of urban conditions and the prevailing winds in the San Fernando Valley result in an insufficiently reliable energy source. The potential use of geo-exchange systems for heating and cooling was also set aside because their application depends on a thorough knowledge of soils conditions and water tables. That required on-site investigations not available at the time. In the 1950s, groundbreaking school design shaped classrooms for natural cross ventilation and daylighting, as exemplified by this cover of Architectural Forum. We've been here before. In some ways, we're rediscovering previous valid ideas, but taking them to the next level. We modeled the potential for improved daylight harvesting in the upper-level classrooms. The use of north-facing roof monitors would provide up to 100% daylight autonomy in the second-floor classrooms. Ground floor light penetration is already aided by light shells, but limited to 20 feet penetration. More dramatic strategies for bringing additional daylight to the lower floor were tabled because of the potential major impact to the fundamental configuration of the classroom wing. As a way of enhancing passive ventilation on both floors of the building, we investigated the introduction of solar-activated thermal chimneys to draw warm air from the classrooms and increase airflow. There are some spatial implications of this component, but also measurable benefits in improved energy performance. A south-facing solar absorption surface is designed to be activated by the sun to create a chimney effect, drawing warm air up and out of the classrooms. This is a detail showing the solar absorption surface on the north side of a thermal chimney. Computational fluid dynamic analysis can be used to analyze wind-driven pressure differentials that affect airflow and inform the dimensioning of the openings in the thermal chimneys. The combination of controlled natural ventilation through perimeter windows or low-level louvers and the use of solar chimneys can also be used as a device to promote night flushing, cooling the building down at night by taking advantage of natural day-night temperature fluctuations in the valley. The same modeling tool is used to predict air movement patterns within the classroom. This diagram underlines the need to carefully integrate roof monitors and photovoltaic arrays to optimize the effectiveness of each feature. In other words, a very well integrated design. This chart shows how the combined measures of adjusted cooling set point, allowing classrooms to get a little warmer, the introduction of thermal chimney, natural ventilation and night flushing, and enhanced daylight can achieve dramatic energy reductions. So as you can see in this chart, cooling loads are reduced by 60%, mechanical ventilation loads are reduced by 44%, lighting loads are reduced by 75%. For the purposes of this study, we have assumed that the combination of energy-producing photovoltaics, when combined with other significant measures, can provide a feasible path to grid neutrality. Given our real estate problems in terms of placing photovoltaic arrays, what is the net photovoltaic capacity required and how much space do we really need to accommodate that capacity? The following charts indicate that by including the other proposed improvements, we can reduce photovoltaic capacity needs by about 98 kilowatts, from 250 to 152 kilowatts total. That is a reduction from 15,000 square feet to a little over 10,000 square feet of roof area. We now begin to have a realistic working scenario which balances the realities of school district-driven mechanical systems, the demands for rooftop real estate for skylights, thermal chimneys, and photovoltaic arrays, and reasonable expectations for the introduction of additional amenities. In summary, in order to achieve success with the goal of grid-neutral schools, energy modeling, design, monitoring, and operating must become a seamless, integrated process. Budget models need to accommodate upfront changes in planning, design, and construction procedures in order to maximize energy efficiency. The introduction of energy-saving measures inevitably impacts the footprint and configuration of school buildings and needs to be accounted for. Performance monitoring of building systems must become an integral part of the scope of services provided by design professionals. Without careful and thorough post-occupancy monitoring, facilities cannot be properly tuned to meet these performance goals. And finally, users need to be educated and trained to ensure optimum and sustained use of the life of the facility. They need to be integral participants in the successful operation of school facilities and can therefore no longer be passive users and consumers.